Welcome to video lecture F2. This one is on the geometry of eigenvectors. I'll be your shepherd, Tom Roby. Here are the outline and objectives. We'll prove that the set of all eigenvectors corresponding to an eigenvalue lambda forms a vector space, which is called the eigenspace of lambda, and sometimes denoted just as E sub lambda for eigenspace. And then I'd like to analyze the action of some simple matrices in R2 and R3. I'd like you to be able to do this to better grasp the geometry of eigenspaces and linear transformations in general. And then finally, we'll prove the very important fact that eigenvectors corresponding to distinct eigenvalues are linearly independent. So here's the proposition. If you've got two eigenvectors for the same eigenvalue lambda, v and w, then any linear combination of those eigenvectors is itself an eigenvector for the same lambda. You may recall in one of the previous video lectures we saw that if you had added two eigenvectors corresponding to different eigenvalues, there's no reason to expect that to be an eigenvalue at all. But if an eigenvector at all. But if you have two eigenvectors for the same eigenvalue, then any linear combination of those eigenvectors will itself be an eigenvector. And what that means then is that if you look at the set of all eigenvectors for lambda, that is a vector space, right? Because to show that something's a vector space, you basically need to show that it's closed under taking linear combinations, under scalar multiplication and addition. And you can check that zero's in there, but so actually in the eigenspace, you have to throw in 0. Even though 0 isn't technically an eigenvector, to make it a vector space, you throw in 0. So that's a technical thing. But the main point here is really just it's a one-line proof. So how does this one-line proof work? Well, if I look at this linear combination, CV plus DW, multiplying by A is linear operator. In other words, the distributive property works. So I can replace A times CV plus DW by C times AV plus D times AW. So the sum splits and the scalars factor out. And now I just use the property that V and W are eigenvectors to replace AV and AW with lambda V and lambda W. But then you can't stop me from factoring the lambda out of this and getting lambda times CV plus DW, which is the vector I started with. So now A times this vector is equal to lambda times this vector. It satisfies the defining equation for being an eigenvector, which means that this linear combination is. And so this will work for any number of vectors, any linear combination you want. And so you get that this is an eigenspace. Okay, so next, let's try to get very concrete here. So suppose that I've got 2, 0, 0, 3. Right? I want to think about that as being a linear transformation from R2 to R2 and understand how it acts. Well, what's nice is this is one of the simplest linear transformations to understand, because if I think about E1 is my E1 is here, and E2 is there. How do these vectors act under the linear transformation? So now if I go over to my image, well, so E1, 2 times E1, this means that E1 goes to 2, 0, and E2 goes to 0, 3. In other words, E1 goes to twice itself, and E2 goes to 3 times itself. So that means that all I've done here is stretch this box out. So this gets stretched by a factor of 2. So this is 2E1 in the image. The height gets stretched by a factor of 3. This is 3E1. And if I wanted to think about, like the unit square area defined by this, I'd be replacing it with a rectangle that had height 3 and area 2. And width 2, and so area 6. Now if this had been a negative 2 instead of a 2, then I would have just flipped this over in the image. So I would have gotten the rectangle flipped over on the other side. Okay? So this is why we like diagonal matrices, because they're really easy to understand, and the eigenvectors of a diagonal matrix are exactly the basis vectors. with respect to which you drew the matrix. So here we assume it's the standard basis. Okay? So in R2, I think we understand everything quite well. So let's go to R3, where we can still draw pictures and make good sense of what's going on. So here I've got 2, 3, minus 5. And so what happens? So I'll draw my picture this way. I've got the z-axis here, the y-axis here, and the x-axis here. X, y, z. And now I'm mapping over here in my image. I've got this axis, and this axis. And maybe I need a new green pen too. That's better. So z, y, x. Okay, and so what's going on with these vectors? So let's see, E1, I'll still make this magenta. And so if this is E1, it's going to something twice as long. So that's good, 2E1. And E2, this vector, is going to something 3 times as long, just like before. And now the z vector, so let's see if I've got another color here. I guess I've got an orange color here. So here's E3. This guy is actually going downward. So this is now minus 5E3. Okay? So if you think about having any vector in R3, what happens? Well, its x component gets stretched by a factor of 2. Its y component gets stretched by a factor of 3. And its z component gets stretched by negative. Gets reflected and then stretched by a factor of 5. Okay? So you can maybe imagine a little cube here defined by these 3 vectors. And it's going to rectangular parallelepiped over here, which, you know, a box basically defined by those 3 vectors. Okay? And of course we know that the volume of that box is the determinant of the matrix, which in this case is easy to compute, or the absolute value of it, 2 times 3 times minus 5. So you get, so this box is going to have volume 30 units, where this is 1 unit. Okay. Let's look at another example. Now, and so the other thing is, what are the eigenspaces in these examples? Well, in each of these examples, the eigenspace is just a line, right? So the eigen E1 is the eigenvector, or an eigenvector for 2, and E2 is an eigenvector for 3, and any other eigenvector is just multiples of those. So in this case, too, in 3-dimensional space, each of these standard unit vectors defines a line, one of these axes, and those axes are the eigenspaces. Okay? But now here it'll be a little bit different, because here I have 2, 2, minus 5. So I have a repeated eigenvalue. So I want to think of 2 as being an eigenvalue of multiplicity 2. And what that does is, let's draw the picture for this one too. So now I've got x, y, z maps to x, y, z. And now E1 and E2 both just get stretched by a factor of 2. Oops. Okay, so what does that mean? Well, that means that any vector in the xy plane will get stretched by a factor of 2, because it's being stretched in the x direction and in the y direction by a factor of 2. And if you just thought about the matrix 2, 0, 0, 2, the 2 by 2 upper part of this matrix, let's see if I can define this for you. Right, so if you just think about that this upper left part of this matrix, that's just saying, that's just the dilation matrix. It just dilates anything by 2. As opposed to 2, 0, 3, 0, 3, which dilates things in different directions further, right? But here, if you take any square in this, it'll become a square here, whereas a square here becomes a rectangle when you stretch different directions by more or less. Now, it's not true. Now, the z-axis is not stretched the same amount as the x and y, but the x and y are the same. So really, any vector, even if I drew some other random vector in here, v, then it's just going to go to 2v over here. Okay? So this xy plane then is the eigenspace, because every vector in here satisfies the property that if I apply the linear transformation to it, I'll just double its length. Okay, so now the z behavior has not changed since what we had earlier. It's still true that E3 here goes to minus 5 E3 down there. Okay? So, and of course, a general vector in R3 will be a linear combination of all 3 vectors. And so, but you can understand one component is just stretching. And sometimes when you're in a real life situation, you may only be interested in what's happening in certain directions. Okay. So finally, we've got one more matrix to look at, which is this one. So in this matrix, let's see if we can think about what's happening. We still have the minus 5 thing going on, but what's happening in the xy plane is a little bit different. So here again, I'll try to oh, this pen doesn't write very well. Is that better? Yeah, good. So there's the upper left hand, well, it takes 1, 0 to 0 minus 1. Okay, so let's see, where am I going to draw this? I guess I will make space here. And now what E1 is doing is rotating to the negative of E2. So this is the image of E1. And E2 is likewise rotating to become E1. Okay? And finally, this guy hasn't changed. It's still going up to E3 here and going down like that. But so try to be clear what's happening here. So you can just tell that E1 goes to 0, negative 1, 0, and E2 goes to 1, 0, 1, 0, 0. That's just saying that these vectors rotate clockwise 90 degrees. And a clockwise rotation won't have any eigenvectors, at least no real eigenvectors. So that means that this matrix only has one eigenvector, only one dimension of eigenvector. It only has only one real eigenvalue. So this is a good example of a matrix that we'll never be able to write in diagonal form, no matter what kind of a basis we use, because it's intrinsic to the geometry of the situation that this, in the xy plane, you're rotating. And when you're rotating, you don't have any vectors which just get mapped to something that's a multiple of them. You always have, the only thing that's fixed is 0, which is not an eigenvector, although it is in the eigenspace. Okay, so I hope this made some sense. So try to do your own examples and think this all through. But it's really useful to see that, what's interesting about this matrix is the way it partitions this way into these 2 blocks means that this xy is a subspace. If you think about the linear transformation just acting on all the variables in the xy plane end up in the xy plane. None of them end up outside of that. So it's an invariant subspace, but it's not an eigenspace. So now let's consider what happens when we have eigenvectors that correspond to distinct eigenvalues. And here the situation is a little bit deeper and quite interesting. If I have a bunch of eigenvalues, v1 through vr, and they each correspond to the eigenvalues lambda 1 through lambda r, which happen to be all distinct. If all of these lambda 1s are, none of these is equal to one another, to any other one, then it turns out that all those vectors will be linearly independent. We'll find this very useful later on when we're trying to diagonalize matrices. And so let me show you how this proof works. Okay, so this is a good example of tying together a bunch of things we know. So suppose I'll write by way of contradiction as a block that these were linearly dependent. Okay. Well, if that were true, then we know that if things are linearly dependent, I mean, we know that we could find some scalar multiple, some linear combination of them that's equal to 0. But we know actually that there has to exist some first vector which can be written as a linear combination of the previous ones. Okay. So that's a fact from before. So then there exists some value k that's in the set 1, 2, ... up to r minus 1, such that c1 v1 plus ... plus ck vk is equal to vk plus 1. Okay? So there's some place where some vk plus 1 that we can write as a linear combination of the previous ones. This has to happen at some stage, because if it doesn't happen before that, it has to happen for the rth thing. Okay? So now, and we can pick k minimal with this property. All right. Now, let's apply a. So I'm going to call this equation star. So let's apply a to star, and what do we get? I always like using different colors, so here we go. So if we apply a to star, then we get a times this equals that, right? So we get a times cv1, c1 v1 plus ... plus ck vk is equal to a times vk plus 1. Okay, but now we can apply, when we apply a to all of these things, what happens? Well, a applied to things, as we said before, distributes, and then a times v1 is going to be lambda 1 v1, and a times vk is going to be lambda k vk. And so this will all boil down to c1 lambda 1 v1 plus ... plus ck lambda k vk. That has to be equal to lambda k plus 1 vk plus 1. Okay? Now, I can also take star and I can multiply it times lambda k plus 1. So what will I get there? So if I do that, then I'll get c1 times lambda 1 minus lambda k plus 1 v1 plus ... plus ck times lambda k plus 1 minus lambda k vk. That's going to be equal to 0, because I'll have lambda k vk plus 1 on the right side, and I'll subtract the same thing. Okay? So you multiply this one by lambda k plus 1, and then you subtract it from this. Okay, so why is this so exciting? Well, this can't happen because the fact that k was minimal meant that there's no way that these vectors v1 through vk have to be linearly independent. And that this is the first time where you get a linear dependence relation. Okay? So the only way this can happen is if all these coefficients are 0. Okay, so I say, but v1 through vk are linearly independent. So what does that mean? In this dependence relation, all those things are 0. So therefore, let me just call these CI. CI times lambda I minus lambda k plus 1 must be equal to 0 for all I. Now, because all of these lambdas are distinct, these differences never 0. Okay, so this guy is not equal to 0 since distinct. And so what that implies is that that must mean the only way this can be 0 is Ci equals 0 for all I. Okay, but now if Ci equals 0 for all I, then that's a contradiction because that means that vk plus 1 must have been the 0 vector. Okay, so that can't happen, contradiction. So therefore, our original assumption was false. We were supposing it was true by way of contradiction, that we could write this. And since we can't, that means that they have to be linearly independent. Okay, so that's the proof of this theorem. It's not that hard. It's just a little bit clever. And I think it's worth commending to your attention because all you do is use the fact that we know that you can always write, if it's linearly dependent, you could write some vector as a sum of the previous ones. And now do two things to that equation, star. Multiply it by lambda k plus 1 and apply a to it. And when you do that, you'll end up subtracting and getting an equation which looks like a linear dependence relation. But these guys are linearly independent. So therefore, the coefficients all have to be 0. And since these are distinct, that meant the original CIs had to be 0. But you see where the distinctness comes in here. If you didn't have the distinct condition, this wouldn't be true. And in fact, we'll see examples where it's completely false. And it throws off our ability to diagonalize a matrix. So one of the things that's great about this theorem is that if you have a matrix which has all of its eigenvalues are distinct, then you know that you're in good shape for being able to find the basis of eigenvectors, which is something that we really like. So for example, if I just write down any matrix like this that's, say, upper triangular, right? So if I write 2, minus 5, 7, 0, 3, 1, 0, 0, negative 1, then I know that the eigenvalues for a triangular matrix are just the elements on the diagonal, and 2, 3, and negative 1 are all distinct. So that means that the eigenvectors corresponding to 2 and to 3 and to negative 1 are all linearly independent. So I have 3 linearly independent eigenvectors. That means they have to form a basis for R3. So we really like it when that happens. And it doesn't happen all the time, but it does happen in some special situations, which we'll be studying actually up until the end of the course. So that's it for this video lecture. Thank you for your kind attention.